Okay, I guess we're all here. Show that oh, it's a little bit bigger.
Are you going to be available for office hours today?
Oh yeah,
What
this
time?
afternoon, this afternoon at 1:30.
Cool. Okay.
Let me call these vectors B1, B2, and B3. Start by showing that these are form an orthonormal basis. Well, we give this a name, call it B if you like. And then express 1, 2, 3 as a linear combination of the basis vectors. So to show that this is an orthonormal basis, you have to show that each of these vectors is length 1. And you have to show that they're perpendicular, their dot product is 0.
Is the 1/3 in the second vector thing, the B2, negative or positive?
It's negative. All the 1/3 are negative, all the 2/3 are positive. So take a moment to do A. Show that the length of each of those vectors is 1. In other words, their dot product with themselves is 1. And show that if you take any pair of them, the dot product is 0. In other words, that they're perpendicular. And since the length of B1 is 1, and I built B2 and B3 with the same three numbers, it's not too surprising that this is also equal to the length of B2, and it's equal to the length of B3. So all three of these vectors have length 1. Let's take the dot product of the first two. Two-thirds times two-thirds. Plus, oh, I can see I'm not going to have quite enough space there. Two-thirds times two-thirds. Plus two-thirds times minus one-third. Plus minus one-third times two-thirds. That's still on the screen. Can you see that? Yep. And that equals 4/9 minus 2/9 minus 2/9 equals 0/9. So B1 dot B2 is 0. Similarly, B1 dot B3, you'll have to do that multiplication. I mean, that dot product can show as 0, and B2 dot B3 show that that's 0 also. So all the vectors have length 1, and if I take the dot product of any pair, I get 0. Is that good? Okay. So B. I want to express this as a linear combination of these three vectors. So some number, which I'll call C1 times that first vector, 2/3, 2/3 minus 1/3, plus some other number times the second vector, 2/3 minus 1/3, 2/3, plus some other number times the third vector, minus 1/3, 2/3, 2/3, equals, where we go, 1, 2, 3. I want to figure out what the C1 and the C2 and the C3 are. So I know two ways of doing that. I have a basis here. So I know I can do this in one and only one way. I could do this the normal way, the hard way. So I could write this as an augmented matrix, 2/3, 2/3 minus 1/3, 2/3 minus 1/3, 2/3 minus 1/3, 2/3, 2/3, 1, 2, 3, and row reduce. I suppose that's not so horrible. This is only a 3x3 matrix. But the numbers are fractions. I guess the first thing I could do is multiply both sides. I could multiply all the rows by 3 and get rid of fractions. So we could do this. And this is how you do it for any basis. I mean, just write the basis vectors down, row reduce into the basis. We'll get the left-hand side down to the identity. And then whatever numbers are here, here, and here, once we get the left-hand side down to the identity, that'll be C1, C2, C3. But since this is an orthonormal basis, I have another much easier option. This you can only do with orthonormal bases. C1 is equal to the vector 2/3, 2/3 minus 1/3, 2/3, 2/3 minus 1/3, dot product with 1, 2, 3. In other words, it's equal to 2/3 times 1 plus 2/3 times 2 plus minus 1/3 times 3 which is 2/3 plus 4/3, that's 6/3, or 2 minus 1, 1. That worked out nicely. And C2 is this vector, B2, 2/3, 2/3, minus 1/3 times 1, 2, 3. So this is equal to, oh, sorry, I put the minus 1/3 in the wrong place. Minus 1/3, 2/3. That second vector. So this is 2/3 times 1 plus minus 1/3 times 2 plus plus 2/3 times 3. So let's see, that's 2/3 minus 2/3, that's 0, plus the 3's cancel out, plus 2, so that equals 2. And the last one, I can do with the dot product also. Let's see, minus 1/3, 2/3, 2/3, dot product, 1, 2, 3. So minus 1/3 times 1 plus 2/3 times 2 plus 2/3 times 3. So let's see, that's minus 1/3 plus 4/3, that's 1, plus 2, that's 3. Oh, that's weird. It has exactly the same coordinates in the second vector as it does in the first, in this basis as it does in the standard basis. Sweet. Okay. But this is only an option if the basis is orthonormal. This you can always do. But if I gave you a basis of R10, row reducing a 10 by 10 matrix, that's a lot of work. Whereas doing 10 dot products, that's not much work. Well, it's certainly a lot easier than row reducing a 10 by 10 matrix. Furthermore, if all you needed was C2, you just have to do one dot product. If all I needed was C2 over here, I still have to do most of the work to row reduce that matrix. So, as I said last time, an orthonormal basis does the main job of a basis. The main job of a basis is to express every vector as a linear combination of the basis vectors. That's its job. It does that easier, better. And that's the end of the curriculum. Okay, so just give me a minute and then we can start our review for the final. Figure about 9 questions with parts. So about twice the length of a midterm, but you'll have 3 times as long to do it. So approximately 2 times as long as a midterm. But you'll have 3 times as long to do it. I will post this on our webpage. At the beginning of exam week, and you'll have till the end of exam week to find a 3-hour slot that you can do this. So take 3¼ hours to do an upload. Finish and upload the exam. So it's comprehensive on the whole course. Show all your work. Comprehensive, show all work. What was I going to say? Oh, yeah. Not everybody has a printer at home, so feel free to work on your own paper. But I will leave space on the exam if you want to work on the exam. So I'll leave space. If you do have a printer, you want to print it out and work in the space that I leave you, feel free. So I will leave space on the exam, so work on the exam or your own paper. Up to you. And then upload to Google Drive. If you can, put all the pages into one file. If possible. And call it, like something like final exam. I don't mean you have to make your own folder and put it in that folder. If you can put all the pages into one file, that would be really great. Not everybody might be able to do that. I don't know if you know how to do that or not. If you can't, don't worry about it. Put the pages in separately. If you could label them, in that case, page 1, page 2, page 3, that would certainly help me. Let's see. Put all the pages into one file, call a file final exam. What other logistics? Oh, you can use a calculator. I don't know how much it'll help you, but you're certainly welcome to use one. You can definitely do that. Are there logistic questions that I haven't thought about answering just because of the semester we're in? Is there something that you want to know about how to do your final that I haven't mentioned? Can't think of anything. I suppose it goes without saying, show your work. I say this to my calculus students because they're sort of new to this, but you guys are all you know,
Yeah,
old.
you already said that on the board. That's like the first thing.
With that?
Second row.
Second
Oh,
row.
yeah. Right, you're right. You're right. I did. Sorry about that.
Well, it's
yeah.
doubly important.
It is important. So here. Now it looks important. Now hopefully we'll forget that I wrote it again. So don't think of what you're writing down as rough work followed by a final answer. That's sort of a high school paradigm. Instead, what you're trying to do is explain to me your thought process. When you write a solution in mathematics class, whether it's this class or any other class, you're trying to lead somebody through to the final answer, have them follow your train of thought. So it's not just scratch work followed by boom, answer. I don't think anybody in this class is going to be doing that because you've had experience in other college math classes. But it would, you would write an essay by, a bunch of random thoughts followed by your concluding statement. That would apply. And so it's the same philosophy here. You want to let somebody who's reading this say, oh, okay, I see how we get to this step, and I see how we get to this step, and I see the thought process behind this. And so I can trust this final answer because I can verify it myself. Okay. So let's see. Some things that are going to be on here. 10:23. I think I'll probably go for about another 10 minutes or so and talk about some things, and then we will continue to talk about some things next time. Because of my next class where some people are giving presentations, I want to get a few things in order before that next class, so we're not going to go the full time this time. So let's see. What's the machine that makes most of our linear algebra course go? What's the operation that you have to, what's this happen? What's the operation that you have to do most often?
Row reduction.
Row reduction. So you all have to be experts with row reduction. So if your row reduction's good, most of your computations are going to be good. So you should be able to convert between what? System of linear equations and a vector equation and a matrix equation and an augmented matrix you should almost not see the difference between those things. So if I gave you the system of linear equations, x plus y minus z equals 1 and 2x plus z equals 3 and minus 2x minus y plus 4z equals 5. That's a system of linear equations. If you were going to write that out as a vector equation, you could write x times 1, 2, minus 2 plus y times 1, 0, minus 1 plus z times minus 1, 1, 4 equals 1, 3, 5. You should look at this, and you should look at that, and as far as you're concerned, they should look pretty much the same. You should be able to write this as a matrix equation. 1, 2, minus 2, 1, 0, minus 1, minus 1, 1, 4 times x, y, z. I know most of the time in this course I used x1, x2, x3, but x, y, z, whatever. That's what I started with up here. Equals 1, 3, 5. And you should be able to write that as an augmented matrix, which is probably the easiest way of all of them of writing it. 1, 2, minus 2, 1, 0, minus 1, minus 1, 1, 4, and 1, 2, oops, 1, 3, 5. Those should all look basically the same to you. And of course, if you were going to solve this, what technique would you use?
Row reduction.
Row reduction, right, absolutely, row reduction. So you do row reduction. Let's say you were doing row reduction, and when you did your row reduction, you got a 1, 0, 0, 0, 1, 0, 0, 0, 1. What can you tell me about the solution to the system?
Echelon form.
Well, that would certainly be an echelon form, but where would you look for the x and y and z? If you got this down
First
to the
pivot
identity,
positions.
yeah, it would be whatever was over here, right? Once you did your row reduction, it would be on the right-hand side of the bar. And how many if you got this down to the identity matrix, what could you tell me about the number of solutions?
Exactly 1.
There'd be exactly 1. Exactly. I mean, yes, absolutely. Let's say when you row reduced it, this didn't go down to the identity matrix. Let's say it went down to something else, another echelon form where maybe the third row or the last 2 rows were 0. If the third row was 0, on the left-hand side of the bar, what could you tell me about the number of solutions? There's one of 2 possibilities.
Infinitely many solutions.
Either infinite or
No solution.
nor solutions. So if this was all zeros over here and this wasn't a 0, there'd be no solutions. If this was all 0 and this was a 0, I mean, if all the 0 rows on the left had zeros on the right, then there would be infinitely many solutions. You'd have free variables. So either you have no free variables, in which case the left-hand side is the identity, or you'd have free variables. Okay. Let's see. So all that stuff. Yeah. Yes. That's basically all chapter 1. Well, no, not quite. Let's say T goes from R3 to R5, and this is a function. What does it mean if we say T is linear? This means 2 things. So T eats vectors in R3 and spits out vectors in R5. If it's linear, what 2 things are true about that function?
That it's linearly independent.
Well, linearly independent describes vectors.
Oh, my bad.
No, it's okay.
Maybe that it's spanning.
Well, spanning also describes a set of vectors.
Oh,
It's closed under addition and multiplication.
Well, the wording you use describes vector spaces, but you're still right. I think what you were trying to say is still true. So 1t of x plus y is the same as t of x plus t of y. It doesn't matter whether you take these two vectors and add them first and then take t of it, or you take t of it and then add them. So this is for all vectors x and y. In what space do x and y exist in? What space? What size vectors does t eat?
3.
Yeah, R3, exactly. And the second thing, so I think when you said it's closed under addition, this is what you meant, that t commutes with addition, actually. And when you said scalar multiplication, I'm pretty sure this is what you meant. That it doesn't, if I want to multiply by c, it doesn't matter whether I take x and multiply by c first and then take t of it, or that I first take t of x and then multiply by c. So these are the two properties of a linear function. When you say something's linear, that's what you mean. So you know derivative is linear. If I have the derivative of a sum of two functions, I can take the derivative of each part separately. If I have the derivative of a constant times a function, I can take the derivative of the function and then multiply by the constant. You know taking derivatives is linear. You know taking antiderivatives is linear. You know taking limits is linear. You know taking definite integrals is linear. Lots of things that you studied are linear. Now, if t happens to be linear, if t going from R3 to R5, what can you tell me about a matrix? What can you say about t as it relates to a matrix? Maybe that was too vague a question. I'm trying to think of how to make it more exact. Let me say it like this. What size matrix can I associate with t? Something by something else matrix, which we'll call A.
3 by 3.
It's, what did you say?
3 by 3.
Not 3 by 3,
n by n.
not n by n.
Oh, is it R3 to R5?
So t goes from R3 to R5. So what size is the matrix? How many rows, how many columns? Rows, columns.
Maybe then 3 by 5?
Close? Guess again.
Oh, 5 by 3.
5 by 3, right. It's a 5 by 3 matrix A, so that t of any vector in R3 equals A times that vector. Linear functions from M to Rn have matrices associated with them. Only linear functions. They're the only ones that have these matrices. So if I want to take if I want to see what the matrix is, it's going to have, well, for one thing, if I want to see its size, since t multiplies against vectors in R3, then this thing has to have 3 columns. And since t spits out things in R5, this thing has to have 5 rows. It has 5 rows and 3 columns. So 5 rows 3 columns. And the first column is going to be whatever T does. So the first column, if A is A1, A2, A3, if these are the 3 columns of A, it has 3 columns, then A1 is going to be, the first column is going to be whatever T does to the vector E1. Remember, E1 is going to be this is going to be 1, 0, 0. And A2 is going to be T2. That's going to be the second column. And A3 is going to be T as E3. That's the third column. So you can always find the columns of that matrix very easily. Just figure out what T does to the various parts, the various unit principal vectors. Okay, how am I doing for time? Oh, I already went over what I said I would do. So we will pick it up here. We'll spend the entire next time reviewing. I will also schedule office hours next week. I know it's Thanksgiving week, but I will be available for questions also next week in case you're going through your studying and you have questions. And I will also have office hours during final exams. I probably won't have office hours right on Thanksgiving itself because I'll be cooking and eating, but the rest of the time probably yes. So any questions before we go? Okay, I will see some of you in 21 minutes, and I will see some of you on Friday.
Can I show you what I made with my project?
Yes. Oh,
'Cause,
hang on.
Because I redid my Excel. I think I thought of something like a little bit better.
Well, hang on. Can I meet you actually in? So this is being recorded right now.
Okay.
So let me meet you in where we usually have office hours.
Okay.